Good morning. This is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. Today we'll discuss a topic in a subject named Refrigeration and Air Conditioning, and this comes for 7th semester Mechanical Engineering students. And the topic that I'm going to discuss, I'm just going to give a introduction to this topic. What is basics of the refrigeration and air conditioning. Now, before going to the refrigeration and air conditioning, there is something called heat engine. We have to understand about what is heat engine. So, the heat engine is a device which takes heat from a thermal reservoir, high temperature thermal reservoir, and it gives some of the heat to a low temperature reservoir, and the difference of these two heats will be given out as a work output in a cyclic process. So the heat engine is a device which undergoes a cyclic process, and during the process what happens is it takes some heat from a high temperature reservoir and gives some heat to the low temperature reservoir, and the difference between these two heat will be given as the work output. Now, here I used a term called reservoir. Now, what is this reservoir means? The thermodynamic reservoir means whatever amount of heat I may take, okay, the temperature of that reservoir, of that body, is not going to change. Okay, whatever amount of heat I extract from the body, the temperature of that body is going to remain same or constant. Then that kind of a body is called a reservoir. Say suppose our oceans are there. So no matter how much water I can take from the reservoir, the level of that river is going to be same. Okay. So this kind of this is a thermodynamic reservoir. Now here two things are there. Now what is this high temperature reservoir? High temperature reservoir, what I am doing is I am taking heat from this. Okay, and the low temperature reservoir I am giving heat. So suppose if I put one truck full of water into the sea, what happens? It is not going to change the level of the sea. So the reservoir is a object or a body from which if I take heat, the temperature is not going to be affected. If I supply heat to that or if I add heat to the reservoir, then also the temperature is not going to change. So here what I am doing is I am taking two such kind of reservoirs. One reservoir is at a high temperature and the temperature is TH, and the other reservoir is at a low temperature TL. Okay. Now this heat engine is a cyclic process. Okay, it undergoes a cyclic process and it will do this. It will take heat during the process and it will reject heat, some of it during the process, and finally it is going to supply some work which is going to be used by the human being. So this is called a heat engine. So the heat engine, so suppose if I connect this heat, say suppose this is a turbine, the amount of work that is given by the heat engine, if I supply to the generator, what happens? It will produce the electricity. So this kind, or if I am giving this to a some kind of machine, what is happening is the machine is going to run and it is going to do some useful work. Okay, so the heat engine, so basically what is heat engine? It is a device for converting the thermal energy into useful work. So there are some examples of the high temperature reservoirs. Say suppose solar energy. So solar energy, no matter how much heat I take from the sun, it is the heat is going to be same. It is not going to reduce the temperature of the sun. So say suppose a oil furnace is there. So the huge oil furnace is there. From the huge oil furnace, we can extract a little bit of heat. What is going to happen? The uh, constantly, if I am putting heat, I mean if I am adding oil to the furnace and the oil is going to burn, what happens is the temperature is going to be constant no matter how much heat I extract from the furnace. Similarly, a nuclear reactor. So the nuclear reactor, once it starts that reaction, it supplies unlimited of, I mean not unlimited, it supplies huge amount of heat. Okay, that heat can be extracted and converted into useful work. Now these heat engines, they convert part of this heat energy to some work, and the work is available in the form of a rotation of the shaft. And that rotation of the shaft, if connected to a generator, we can convert into electric energy. So the reject remaining waste heat to the low temperature sea. So part of the energy is converted to work, and part of the heat is converted to the work, and part of the heat is rejected to the atmosphere. So the atmosphere here is considered the low temperature reservoir. So TL is the temperature of this. So this here one cycle is there. So this is a turbine, heat exchanger, pump, heat exchanger, turbine. So any fluid is going in this cycle, it will. So here in this heat exchanger, what I am doing is I am taking heat, and in this heat exchanger I am rejecting heat, and the pump is connected to this turbine so that the fluid can be circulated inside this circuit, and the remaining work is transferred out to the generator. So this is the basic working, or the schematic. The picture is showing the schematic of the heat engine. So it is explaining the basic principle of heat engine, how it works. Now here there are few terms called Q in. So what is the amount of heat that is taken by the heat pump during the cycle process? And Q out is the amount of heat rejected by the heat engine into the atmosphere during the cyclic process. So the net work that the heat engine develops can be written as the heat input minus heat output. So this is the net work. In a formula manner, you can say that this is the net work that the heat engine can develop. Now, I said this undergoes a cycle. Okay, and here is one cycle. It is a Carnot cycle. So the Carnot cycle is an ideal cycle because it is having all irreversible processes happening in this. So two constant heat absorption, the constant temperature heat absorption and constant temperature heat rejection process are happening, and two isentropic work isentropic expansion and isentropic compression happens. So what happens here in these two isentropic means the entropy is going to remain constant, and the isothermal means the temperature is going to remain constant during the process. Okay, the entropy is going to remain constant in isentropic process, and temperature is going to remain constant in isothermal process. Now, as I said, this Carnot engine, it assumes that all the processes are reversible processes. So what do you mean by reversible process? Say suppose if I am the fluid flows from here to here, okay, the fluid flows from here to here, it will extract heat. Say suppose if it is going in a reverse direction, the heat will be rejected, and the amount of heat adding or rejection will be the same. Okay, so that is the, say suppose if I am doing some work, if I am rotating this, what happens? Some work will be spent on this. Now, if it rotates on its own, what happens? The work will be developed. So, the reversible process, how this reversible process happens are infinitely small time interval. Say, suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like that. There are number of time intervals are there during this is the entire duration of the process, and the process happens in small time interval. So what happens is, from here to here the process happens and the entire system comes to equilibrium, and again some process happens, again it will come to equilibrium, and again some process happen, and again the entire system comes to equilibrium. So like that, at infinitely small intervals of times, what happens is the process executes, and at each interval it comes back to the, it becomes in equilibrium position, and again go to the next time step, and again it will become equilibrium, and again it goes to next time step, and it will come to equilibrium condition. So, but ideally speaking, this kind of process is not possible. But these are a theoretical process or hypothetical process, and they are called reversible process. So, the reversible process that are taken into consideration by Carnot in his cycle called Carnot cycle. Now here I said two constant temperature, heat rejection, and two constant entropy work process are happening here. So here in the turbine, say suppose one turbine is there and the turbine is supplying some work, and the compressor is there and the compressor is taking some work from the turbine. So the turbine is providing some work, and part of the work is given to the compressor so that the circulation happens, and the remaining part of the work is given out as output. So the net work given out by the heat engine is equal to work output of the turbine minus work input to the compressor. So this is another formula. So previously we have seen it is a difference between the heat taken and heat rejection. So the net work done is equal to heat, I will write here. So it is Q in minus Q out. So in problems they make you work in, work out, or heat in, heat out, and they will ask you to find what is the net work done during the process. So this is the explanation for the Carnot cycle. Now here you see. So the Carnot cycle, because since we are assuming that all the process are reversible process, the Carnot cycle is known as is considered as the best or ideal process, ideal cycle. Okay, the Carnot cycle is considered as the ideal cycle because all the process that are taking place here are considered to be the reversible process. Okay, so what are the two reversible process? The two isothermal process are there and two adiabatic or isentropic process are there. So here this is a constant temperature. So this is a constant temperature process and this is a constant temperature process. During this process, it is taking heat from a high temperature reservoir, and during this process, it is giving heat to a low temperature reservoir. Now here, this is a constant entropy process and this is a constant entropy process. So in this process, the work is given out, and in this process, the work is taken by the compressor. So the net work by the heat engine will be the area under this curves. Okay, this shaded portion is graphically representing the net work done by the heat engine. Okay. Say suppose if I don't want uh, this heat out, if I want to eliminate, then if I eliminate, then it becomes a steady flow process. So the steady flow process means the fluid is taken into the compressor, fresh fluid is taken into the compressor every time, and whatever is remaining into the in the turbine, what I mean after the extracting work from the fluid is rejected to the some kind of sump. So what happens here is you cannot extract maximum amount of energy when you are using a steady flow process. So the generally we consider it as a closed cycle process, and this is called a closed cycle closed cycle process, and the process is given by scientist Carnot, the name called the Carnot cycle. Okay, the Carnot cycle. Now here we have discussed about the Carnot cycle, how it functions. Now what we'll see is the efficiency. So what is the thermal efficiency of this hypothetical Carnot cycle? It is not an actual process, it is an imaginary process. So it is called a hypothetical Carnot engine. So here Q in here is the amount of heat taken by the heat engine from the high temperature reservoir. This is the high temperature reservoir. So I am naming it as QH. So the high temperature reservoir, whatever heat is taken is Q in case of a heat engine. Now Q out is the temperature rejected by the heat engine to a low temperature reservoir. So I am giving as a QL. I am taking this as a QL, heat given to the lower temperature reservoir or low temperature reservoir. Now what is efficiency? So the efficiency is, what is the main purpose of this engine? I need a network. Some work output should be there for the Carnot engine, and the net work is the desired output, and the input is the heat supplied by the high temperature reservoir. So the efficiency, thermal efficiency is equal to the net work supplied by the heat engine divided by the net heat taken by the heat engine. Now in the previous slides we have seen that net work done is equal to QH minus QL, okay, or Q in minus Q out, okay, Q in minus Q out or QH minus QL in this particular case. Now if that is the work net work done, so if I take QH minus QL divided by QH, what happens is this QH will get cancelled and you will get 1 minus QL by QH. So this is the formula for finding the thermal efficiency of a Carnot engine. Now this thermal efficiency can be expressed in terms of a temperatures. Okay, since we are assuming that this Carnot engine is having the reversible process, so the reversible process Q is proportional to L, you can take. So Q is proportional to T. So if I substitute that T in place of Q, what I can get is thermal efficiency is nothing but TH minus TL by TH, or 1 minus TL by TH. Either way you can write. So if in any problem, if the question is asked, say, stating the high temperature of the higher temperature reservoir and the temperature of the lower temperature reservoir, then easily you can find out what is the efficiency of the Carnot engine. Okay, so what is the efficiency is found out using this formula. And since this is a reversible process, the efficiency of the Carnot engine is the maximum possible efficiency within while working between these two temperature reservoirs. Say suppose I have two temperature reservoirs, high temperature and low temperature, and I have many engines with me. So the when I compare the performance of all the engines, the Carnot engine, if I can develop, will give the maximum efficiency. So the Carnot engine is considered as the ideal reversible engine for reference of all types of heat engines. Okay. Now we will solve one problem based on Carnot heat engine. So here in the problem it states that it receives, okay, the Carnot heat engine receives 500 kilojoules of heat per cycle. Per cycle is important. So it is for one cycle, how much heat it is taking? It is taking 500 kilojoules, and from high temperature reservoir. So there is a high temperature reservoir, and the reservoir temperature is 652 degrees centigrade, and it is taking an amount of 500 kilojoules from this reservoir. And what it is doing is it is rejecting heat to a lower temperature reservoir. Okay, it is rejecting heat to a lower temperature reservoir, and the lower temperature reservoir is 30 degrees centigrade. So in this problem, what he is asking to find what is thermal efficiency of Carnot engine. So thermal efficiency, it is very straightforward. I can use this formula 1 minus TL by TH. Now here many students will do mistake. So what they will do, they will take the temperatures and substitute here. Okay. But here what is the caution that we have to take is, we have to substitute the temperature in kelvins, not in degree centigrade. So if I convert the temperature into Kelvin, I have to add 273 to the centigrade values. So if I add 273 to 30, I will get the temperature in Kelvin. Similarly, if I add 273 to 652, I will get a temperature in Kelvin. Now, if I substitute all this and I do simplification, it is very straightforward, and I will get the value of 0.672. So, this the first bit is pretty straightforward. So, directly I can substitute and I can get. So, sometimes what I will ask is the amount of heat rejected to the sink. So, QH is given and is asking QL, what is the heat rejected. So we had another formula for thermal efficiency, and that thermal efficiency formula is 1 minus QL by QH. Now already I have found out what is thermal efficiency, and that is equal to this. Okay, now if I use this thermal efficiency here in this formula, and I know what is QH, I can easily find out what is QL. So what I have to do, I have to bring this QL by QH this side, and thermal efficiency this side, then QL by QH is equal to 1 minus thermal efficiency, and thermal efficiency I have already found as 0.672. Now this 0.672, if I subtract from 1, I will get 0.328. And if I multiply that with the 500 kilojoules, I will get the amount of heat rejected to the sink. What is that? That is equal to 164 kilojoules. Say suppose, okay, so this thing we have seen. For suppose if he is asking you what is the net work output per cycle, how to find? Here in this question he has not asked what is the net work output. But if suppose they is asking you what is the net work output, how to find? So the net work output, as we already know, is the formula given by QH minus QL, and that is equal to 500 minus 164 and this is equal to 6, 3, 3. So it is a 336 kilojoules per cycle. Okay. Say suppose if if the mass amount of fluid that is being circulated is given, I can find out how much of energy is produced, how much of work is produced per second. Okay, this is kilojoules, and it is for one cycle. This is the heat, work done, work supplied by the heat engine per each cycle. Okay, very simple. If temperatures are given, high temperature, low temperature, higher temperature reservoir temperature is given, and low temperature reservoir temperature is given. I have to convert that into Kelvin and substitute in this formula. I can get what is the thermal efficiency of the Carnot heat engine. Now, once I know the thermal efficiency, I can substitute back in the formula having the heats, and I can find out what is the heat rejected by the, either if what is heat rejected is given, I can find out what is the heat supplied, and if heat supplied is given, I can find out what is the heat rejection. Once I know these two values, I can easily find out what is the net work supplied by the heat engine. So this is a problem based on Carnot heat engine. So far what we have discussed is about heat engine. But the topic, the topic that is related to the refrigeration and air conditioning subject is starting from here. What is it? It is a heat pump. So what is this heat pump? It is the reverse of the heat engine. Okay, it is the reverse of the heat engine. So the heat pump is a reverse process of the heat engine. That's why what we have discussed till now is the heat engine. So once I know what is heat engine, I can easily understand what is a heat pump. So what is happening here in heat pump is, by supplying some work, by supplying some work to the heat pump, what I can do is I can extract heat from a low temperature reservoir and supply the heat to the high temperature reservoir. Okay, so what I am doing is I am supplying some work, and with that work what I am doing is I am extracting some heat from the low temperature reservoir and supplying that heat to a high temperature reservoir. Now you can ask me, why, what is required for heat engine, heat pump? Directly I can use a heater. We will see that. Okay, so here if this heat pump is working based on the Carnot cycle, reversed Carnot cycle, then it is called a Carnot heat pump, and these remaining things are similar. See, heat out, Q out is amount of heat rejected by heat pump, and Q in is amount of heat taken by the heat pump, and the net work that is supplied to the heat pump, here it is heat pump, the net work given to the heat pump is equal to Q in minus Q out. Which is greater, Q in or Q out? So the maximum one minus minimum. Now I have asked one question. So we have a doubt. So sir, I have a heater, directly I supply some power to that, and it is producing some heat. You can ask like. Now we will see here what is happening. What is happening here is, in the previous thing we can see, it is say suppose 164 amounts of heat is taken from this lower temperature reservoir, and I am supplying only 336. Okay, 336 amount of kilojoules heat I am supplying to the heat engine. So what is the amount of heat that I can supply to the room which I am going to heat? It is the sum of these two, and that is equal to 500. Okay, directly if I use the heater, what happens is I can supply only 336 kilojoules to the room. So the room will get heated up with an amount of 336 kilojoules only. if I use a simple heater. Now, because I am using the heat pump, what is happening is I am getting an extra amount of 164 kilojoules of heat from the atmosphere. I am taking the heat from the atmosphere and I am giving to the heat to the room. Okay, so what is this heat pump doing? It is taking the heat from the atmosphere and supplying to the room, so that the room is maintained at a some higher temperature than the surroundings. So this is generally required in case of the low, the places where the temperatures are very low outside. Okay, say suppose if I go to some Canada kind of places, or Ooty, or Kashmir kind of places, outside some time, some period of the year there will be snow outside. So when there is a snow outside, if I want a comfortable place inside the room, comfortable temperature inside the room, what I have to do? I have to heat up the room. So in that process, what is doing, instead of taking a simple heater, what I am doing is I am extracting an additional amount of heat from the outside surroundings, and I am adding that heat to the room, and in that way I am maintaining the temperature of the room at some higher temperatures. So this is the purpose of heat pump. Now we will see a similar one, that is called refrigerator. Now what is this refrigerator doing? Okay, the room is to be made, the previous one heat pump, the aim is to keep the room at a temperature higher than the surroundings. Okay, now what is the refrigerator purpose? So I am inside this room and I want this room to be kept at a temperature lower than the temperature of the surroundings. So what I am doing is I am taking some heat from the room and supplying to the atmosphere outside. Okay, I am taking some heat from the room and supplying it to the atmosphere outside. So if I consider this portion, it is a refrigerator. Okay, if my focus is on the low temperature reservoir, or keeping the room at a temperature lower than the atmosphere temperature, then it is a refrigerator. If my purpose is to keep the room very hot, hotter than the outside temperature, then this is a heat pump. Okay, if my focus is, my room is the higher and the surroundings are at lower temperature, then it is the heat pump. And if my room is at lower temperature and the surroundings are at higher temperature, then it is called, the same machine is called the refrigerator. So the same refrigerator works as heat pump or refrigerator. Okay, the same machine works as heat pump or refrigerator. What is the main difference? What is our aim? The aim is whether to keep the room at a temperature lower than that of the atmospheric temperature, or whether I want to keep this room at a higher temperature than the atmosphere. Okay. So here this heat pump, this is room and this is atmosphere. And in refrigerator, this is atmosphere and this is a room. Okay, so this is the difference. So the aim is, if the aim is to keep the room cool, okay, so my focus is how much heat I can remove from the room. If the aim is to keep the room hot, my focus is amount of heat I can supply to the room. Okay, so there is a term called coefficient of performance. So the machine is doing some work, it is performing some action, and what is the coefficient of performance of this machine? So the coefficient of performance is equal to, here in both cases I am supplying some work. Okay, so that work will be on the denominator. Okay, now if I want find the COP of a heat pump, what I have to do? I have to take what is the amount of heat I am supplying to the room. If I am finding the refrigerator, what I have to do? I have to find what is the amount of heat I can take from the, what is that, from the room. Okay, so here the heat is taken from the room and supplied to the atmosphere, or heat is taken from the atmosphere and supplied to the room. So if there is an interesting fact here. Okay, so if what is work here? What is the net work done? Net work done is nothing but QH minus QL. This is equal to net work done. Okay, QH minus QL is a net work done, that we have already seen. Now, what is the relationship between the COP of refrigerator and COP of a heat pump? From this you can find out. So what is the what is QH by Q net? So what I am doing is I am bringing this one here, 1 minus QH by net minus QL by W net. So what is this here? 1 is equal to COP. What is QH? QH by work net is nothing but COP of heat pump minus QL by work net is nothing but COP of refrigerator. So the difference of the coefficient of performance gives me a value of 1. Okay, or I can say that if I add COP of heat pump, COP of heat pump is equal to 1 plus COP of refrigerator. Why this relationship is very important? This relationship is very important because in some cases, as I already said, the same engine is working and the aim is different. Okay, so in questions what they will do is they will say that the COP of a refrigerator is so and so, or they will give some conditions and ask you to find us what is the COP of the refrigerator. And again in the next step, next bit, what they will ask is, if the same machine works as a heat pump, okay, if the same machine works as a heat pump, what is the COP? So if I know what is the COP of refrigerator, I can find out what is the COP of a heat pump directly from this relationship. So the COP of heat pump is equal to 1 plus COP of the refrigerator. Okay, so we'll see some problems in the next class, and then we'll see further into the further topics of the actual refrigeration cycles and actual there are two types. One is a vapor compression cycle and vapor absorption cycle. We'll see those two cycles in the future coming classes. The content for today's class is taken from the CP Arora, the Refrigeration and Air Conditioning textbook by Tata. The manufacturer is the publisher is the Tata McGrail Publishers, and it is the 4th edition which I have taken. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.